In this video, I'm going to show you how to do a chi-square test for testing independence in two-way tables. We're going to start with this problem here. In this problem, we have a table that summarizes a data set that examines the responses of a random sample of college graduates and non-graduates on the topic of oil drilling. Complete a chi-square test for these data to check whether there is a statistically significant difference in responses from college graduates and non-graduates. So a two-way table, like the one shown here, summarizes count data between two variables. Okay? So a number of college graduates were asked whether they support, oppose, or don't know oil drilling. And then a number of non-college graduates were asked the same question. And the number of people that answered yes, that they are college graduates and that they support, is 154. And for example, this number 126 represents the number of people that were not college graduates and they opposed oil drilling. And what we'd like to know if there is a dependence on these two variables. Support, oppose, don't know on the topic of oil drilling, that's one variable, and whether or not a person is a college graduate. So this is a standard hypothesis test. So the first thing we're going to do is we're going to remind ourselves as to the four parts of hypothesis testing. The first part is, of course, to identify what are the hypotheses. And we're going to learn how to write the null hypothesis and the alternative hypothesis. In step 2, we're going to calculate the test statistic, which is going to be a chi-square value. In step 3, we're going to look at the critical value from the chi-square table, and we're going to estimate the p-value. And based on that, in step 4, we're going to make our decision whether or not to reject or fail to reject the null hypothesis. And of course, we can make our conclusion and write a sentence to answer the question of statistical significance. So let's start with the final part. After we've done all the analysis, we're going to choose one of these two answers. In this first answer, we're going to say that the data do not indicate a statistically significant difference at the 5% level of significance if we were to find a p-value that is greater than 0.05. In other words, we would fail to reject the null hypothesis that says that support for oil drilling between college graduates and non-college graduates is independent. Or, if our data did have, we would say that the chi-square test of independence was conducted and the data indicate a statistically significant difference because we would get a p-value that is less than 0.05 or even less than that. So that would mean that we would reject the null hypothesis, and basically we would say that yes, there is a statistically significant difference in responses from college graduates versus non-graduates. But at this point, we don't know. And what we're going to learn is how to analyze the data in the two-way table to make this determination. So back to the beginning, let's write down our hypotheses. The null hypothesis basically says that these two variables are independent. So maybe we can say that response for oil drilling and education level are independent. Okay, and the alternative will say that the response and education level are dependent. Okay, now another way of writing the null hypothesis might be that there's no difference in responses from college graduates and non-college graduates. And the alternative hypothesis saying that they are dependent, another way might be to say that there is a difference in response from college graduates and non-graduates. So, these are the null and alternative hypotheses. Okay? The next thing is to calculate the test statistic. What this test statistic is going to do is it's going to tell us, if there is a difference between these two columns or between these three rows. Now, what we have here in this table is we have the observed counts. After doing the survey, these are the observed counts we got. So what we want to calculate is, under the assumption of independence, which is under the null hypothesis, we want to calculate the expected counts. So in other words, if we assume that these two variables are independent, what would the expected counts be? Okay, and so let's move this over just a little bit. So the way we calculate the expected counts requires us to first figure out the row total and column totals of these two rows and column variables. So the row total is straightforward. For example, to get the row total here, we would just add 154 plus 132, which gives us 286. The row total for the second row would be 180 plus 126, which is 306. The row total for the third row would be 104 plus 131, which is 235. And then the column totals, so for the yes column, we're going to add 154 plus 180 plus 104, that's 438. And for the second column, we get 389. Okay, so these are totals. Those are the row totals. These are the column totals. And what we need is one more thing. We need the grand total. So the grand total, you can just add the row totals or you can add the column totals. Either way, you'll get 827, which is how many people were in this survey. Okay? Now, back to our main task of calculating expected counts. Now, let's focus on this outcome. A person says yes and that they support. So if we assume that these two variables are independent, the expected count for support and yes would be the row total for that cell, this is a cell, times the column total for that cell, divided by the grand total, which is how many people were in the survey. Okay? So the row total for that cell is, of course, 286. So that would be 286 times the column total for that cell is 438. 438. And divided by the grand total, and the grand total is of course 827. And if you do the calculation, you end up with 151.5. Okay? And you do the other cells similarly. So let's now take a look at 126 observed count. So that's the oppose and no. The expected number of outcomes, if we had surveyed 827 people, and we assume independence, would be again the row total for that, which is 306, that's 306 here, times the column total, that's in this column here, which is 389, divided by the grand total, which is again 827. And if you calculate that, you end up with 143.9. Okay? So what I like to do is I like to put in parentheses next to the observed count what I got for the expected count. So the expected count for that 154 cell is 151.5, and the observed count for the 126 was 143.9. Pause the video here and see if you can calculate the expected counts for the other remaining 4 cells. Okay, welcome back. So here in this table, I've calculated all the expected counts and I've summarized them in parentheses in the table. Now, what we'd like to do is we'd like to figure out if the observed counts are close or far from the expected counts. Okay? As you can see probably that this observed count and this expected count are not too different. Okay? But on the other hand, perhaps these two are a little bit different. And we want to see if this difference is just due to randomness or is it due to them being dependent. Okay? Now, there is a systematic way to figure this out, and that is to consolidate those differences like this. So what we're going to do first is we're going to make a table that has as its first column the observed counts. So we'll just write them down in rows. So the first row is 154, 132. The second row is 180 and 126. The third row is 104 and 131. Then we're going to write the expected counts. So that's what we calculated, 151.5 and 134.5 in the first row, 162.1 and 143.9 in the second row, 124.9 and 110.5 in the third row. And one of the things that we'd like to do is we'd like to add these up to make sure that they're going to add up. This of course adds up to 827. Of course this has to add up to 827, and it does. You should check that. Let's write down expected here. Okay, and here is the main calculation that's going to figure out if there is a difference between these two. It's going to measure that. So you want to take the observed minus the expected count, square it, and divide it by the expected count. And we're going to do that for each of these values. So, for the first one, so let's do that for the first one. So here, the value that's going to come out is basically applying that formula. So we have the observed count is 154 minus 151.5 is the expected count, squared, divided by the expected count. Okay, so once again, the observed count goes here, the expected count goes here, the quantity is squared in the difference, and the expected count goes in the denominator as well. So now, if you calculate this, you end up with a measure of the difference of these two values. And this one happens to be 0.0413. So I can copy that here, 0.0413. And I can repeat this for each of the other observed and expected pairs. Okay? So pause the video here and see if you can complete that table. Okay, welcome back. So I've calculated the other values, and this last value here is of course the sum. And this sum that we get of the third column is actually our test statistic value. So our test statistic value is chi-squared equals 11.4696. Now, of course, as you probably remember, the test statistic, the chi-square distribution, has a parameter called degrees of freedom. And so that's important for us to find the critical value later. So let me show you how to find the degrees of freedom for the chi-square test of independence in two-way tables. It's going to be the number of rows minus 1 times the number of columns minus 1. So in this table, there are 3 rows, so that would be 3 minus 1, times there are 2 columns, yes and no, so that's 2 minus 1, so that's 2 times 1, which is 2. So the degrees of freedom here is 2. Okay, and this is your test statistic value that we got from the data. Now, in chi-square tests, the larger this chi-square number is, the more likely it is to reject the null hypothesis, because it indicates a difference between observed and expected. And the expected was under the independence assumption. So if there's a difference between the observed and the expected, then that independence assumption might not be due to chance, or the difference in values might not be due to chance, but rather to there being some dependence. So we would reject the independence if this number is large. Okay, so let's see how to determine that. So over here, we have a screenshot of the chi-square distribution, and we'd like to focus on the 2 degrees of freedom row because our data requires 2 degrees of freedom, and the cutoff for us is going to be to look at the 5% significance level. Okay, and that number happens to be 5.99. Okay, so here's 5.99 on the chi-square distribution. Okay, this is the chi-square distribution with 2 degrees of freedom. Okay, now the test statistic value that we got was 11.46, which is way far to the right. So the chi-square value that we got is right here. So clearly we are at a p-value of less than 0.05. Okay, so we're definitely going to reject the null hypothesis. So we're going to reject independence. Okay, but we could say even more here. If you go as far as 0.005, you can see that the critical value at 0.005 is 10.6, and our value is still even higher than that. So this tells us, since our test statistic is higher than the 0.05 critical value, that tells us that the p-value is less than 0.05, but actually this tells you that not only is p less than 0.05, it's also less than 0.005, okay, which is a very small p-value. All right, so we definitely reject, and when we are reporting, we want to report the smallest p-value that we can from our table. Okay, now it's not less than 0.001 because our test statistic is not smaller or is not bigger than 13. Okay, all right, so here we have put everything together, what we have observed in the previous slides. And we've added one thing, which is our statement about the rejecting the null hypothesis at the 5% level of significance in favor of the alternative. Okay? So based on this analysis now, we are ready to see which checkbox works. Okay? So we know that we have to reject the null hypothesis, and so this is the correct answer. There's a typo here, let's fix it. The data do indicate a statistically significant difference in responses from college graduates and non-graduates at the 5% level of significance, and the chi-square test statistic value goes here, which is 11.4696. And the p-value we said was even small, 0.005. Okay? And that is how you conduct a test of independence in two-way tables.